Okay, welcome back. Today we're going to be talking about Chapter 1, Relations and Functions, continuing on to Section 1.2, Relations. A relation is simply a set of points in the plane. We talked a lot last time about intervals and other sets of real numbers. Today we want to talk about the set of points. Now, because a point has two coordinates, an x and a y typically, we would call the set of all points R2. R because I have real numbers, 2 because I've got two coordinates. If I want to graph a relation, I simply plot all of the points in the set. In this case, all I've got here is the point 2, 3, negative 1, 2, and 1, 2. Plotting these points is very simple, and the graph of the relation is just 3 points. But most of the time, the graph of a relation is going to be more complicated. That means that I'm going to potentially have, rather than a list of a couple of points, a set builder notation that's going to describe the entire rule. So let's take a look at an example here. Here I have the relation R1 is x, 3, and then it gives us a rule for x. So what we can think about here is the rule for x and the rule for y. Starting with y, the rule for y is that y is simply equal to 3. Now you might think to put this right here, but this is not quite correct because while y is 3 there, that doesn't necessarily follow the rule for x. Since we need to put the rules together, what I like to do is I like to go off to the side and remind myself of the rule visually to the side, but we'll come back and deal with it later. The rule for x is a little more complicated. In this case, x is between 1 and 4. We've seen this before in interval notation, 1 to 4, including both endpoints. So I can sketch that kind of interval down at the bottom here, representing x. Now what I need to do is I need to overlap both rules together. What that means is that I want to consider y coordinate of 3 only and x coordinate from 1 to 4. This, for example, has an x coordinate of 1 and a y coordinate of 3. And this has the x coordinate of 1 and the y coordinate of 4. I'll connect the dots, and this is my actual final answer. The purple and orange that I've got off to the side and down to the bottom, those are not part of your final answer at all. Looking at another example here, I've got the exact same idea, but this time I've not included 4 for x, which means that in my plot, all I'm going to do is the exact same thing as last time, but I'll have an open circle here. This circle is open because even though the y coordinate is 3, the x coordinate is 4, and we do not want to include that. Let's try an example with more rules here. This time, I've got a very similar rule that I've put on y from 1 to 4, but I don't actually have a rule for x at all. If there's no rule for anything in set builder notation, you can assume that it can be anything it wants. In other words, I could treat x as if the rule for x was written x is any real number. X is in the set of real numbers. And if I was going to draw that on the number line, it would be everything. My rule for y is actually the same rule I had for x both times, so it'll look a little familiar. However, it's going to be vertical this time rather than horizontal. Now, to combine these two rules together becomes a little bit more complicated because rather than simply plotting a line segment, I've got this big shaded area. So the first thing I'll notice is that anything at all in between 1 and 4 in y coordinates will work. So I will have all of this area being valid area. And you can shade that in however it works best for you to shade. Along the bottom, I do want to include the points where y is equal to 1. All of them, again, because our rule for x has no restriction. So I might draw that like this. Let's make it a little bit neater. A solid line to represent the fact that I go all the way down to 1 and include it. On the top, since I don't want to include 4, I'm going to use a dotted line. This represents the fact that I want to get right up to 4 but not include it. And remember that we need to include all the stuff up to 4, so that's 3, 3.5, 3.9, 3.99, as close as you can get. That's why we use a dotted line rather than simply stopping before. The dotted line represents the fact that we go right up to 4, but we don't actually hit it. The dotted line plays the same role that the open circle plays, just as the solid line plays the same role as the filled circle. And the shaded area plays the same role that the line did when we were doing one-dimensional segments. Now, in this case, we want to look at two specific examples, a straight vertical line and a straight horizontal line. In this case, I'm just going to use set builder notation. So for the vertical line, I need to follow a line that goes through the point A, comma 0. Let's say for the purposes of example that this was our point A. Nope, sorry, this will work better as our point A. And the vertical line is just going to go like this. Now look at all of the points for the line. In terms of x coordinates, all of the x coordinates are A. In terms of y coordinates, I see that the y coordinate can be anything. So if I was going to write out the set for this, there's a couple ways I could do it. I could simply write A, comma 0, or excuse me, A, comma y, where y is a real number. Or because we usually know when we're writing out points that it's going to be two coordinates of reals, I could just write A, comma y. Typically, this would be for a fixed number. So for example, in this example, if my A is about 2.5, then I might write out the set as 2.5, comma y. You may have seen the equation for this line before. The equation for this line, since x is a fixed number, but y can be anything, would be x is equal to 2.5. We'll look more closely at the equations for lines in later sections. We can do a very similar thing for flat horizontal lines. This time, it's the y coordinate that fixed. I picked 5 in this example. So I might pick for this the set x, comma 5, where x is real, or in shorthand, maybe simply x, comma 5. And the equation would be y equals 5, because in this case, y is fixed. All of the y coordinates on this line are 5, whereas the x coordinates vary as I move left and right. Now, to graph an equation, we're going to graph all of the points that satisfy the equation. That's going to form a relation, which is going to be a picture on the graph. We can look at an example here of an equation. X squared plus y cubed is equal to 1. And we can go ahead and do a sketch of the graph. So the first thing we want to do before we go on to the graph itself is actually write out some set notation here. So if I was going to write a set for this, remember the first part is always the format. Since I'm trying to look at a graph of points, the set is going to be a set of points, and so I'm looking at x, comma y. Then I'll put the rule, and here the rule is that x squared plus y cubed is equal to 1. Thinking back to our last lesson, I first start with the form. I'm looking for points, so I need to describe what a point looks like. Then I'm looking for the rule, and the rule is simply given by the equation. To check if a given point is on the graph of an equation, I simply plug in the values. So in this case, for example, I have 3 squared plus negative 2 cubed equal to 1, and we'll check and see if this is actually true. Evaluating this, I get 9 plus negative 8 is equal to 1, and that is true. 9 minus 8 is 1. So this point is on the graph. If I plug in 0, 0, 0 squared minus 0 cubed, is that equal to 1? No, it isn't, because I get 0 minus 0, which is equal to 0. So this is not equal to 1, and so 0, 0 I know will not be on the graph. Now, we are going to look at lots of different techniques for graphing some standard equations. Most notably, we're going to be looking at lines and parabolas, and potentially much further down the road, exponential equations and logs, and maybe even some 3D equations. But for now, what we want to focus on is we want to simply focus on graphing an equation by plugging in points. So we'll make a table of values. Let's just plug in a couple of different values for x and see what comes out for y. So for example, if I plug in 0 for x, then I would get 0 squared plus y cubed equals 1. If y cubed equals 1, then y must equal 1 as well. So 0, 1 is going to be 1 point on my graph. I could similarly plug in and see what happens if x is equal to 1. In this case, 1 squared plus y cubed equals 1. Canceling out the 1's from both sides, y cubed equals 0, and I get out 0. I can also plug in minus 1, and I will get the same answer. We can plug in a very large number of points here. We saw, for example, that I had the point where x was 3 and y was -2. We would also have the point -3, -2. There's no limit to how many points we could plug in. We could keep plugging in numbers for x and y and see what comes out. I'll always try to be very clear when asking how many points I want you to plug in, or I'll ask you to plug in some specific points. We can plot each of these points, so it looks like x and y each go up to at most 3 in either direction. Be sure when you're drawing your own graph to label your axes. So I'll put x and y, and then 1, 2, 3, 1, 2, 3, to make it clear that my scale is 1. And then I'll plot each of these points. So I've got 0, 1. I've got 1, 0, and -1, 0, which is here and here. And then I've got 3, -2, and -3, -2. So that'll give me here and here. And this is starting to give me a little bit of an idea of what this graph might look like. Kind of like an upside down U that opens up maybe a little bit wider. We could plug in way more points to get a better idea, but typically when it's an equation that we're not really sure how to approach, we might use a graphing calculator. Now, I will want you to be able to plug in points, and for specific problems that focus on things that we learn, of course, I won't want you to use a graphing calculator, especially on the exams. But we will be allowed to use graphing calculators in some points, and we'll of course want to know how to use them so that we can use them once we get finished with this class and we go on to the real world. Now, intercept is a specific thing that we can use to start analyzing a graph. An intercept is where it crosses one or of the two axes. We can have an x-intercept and a y-intercept. So if the graph goes through the x-axis, we would call that the x-intercept. If it goes through the y-axis, we call that the y-intercept. Taking this graph again, let's make a copy of this graph. Bring myself down a version that we can look at right next to this definition. Gotta do a lot of scrolling here. This graph I see has the point 0, 1 is where it crosses the y-axis. So that would be the y-intercept. In this case, I have two x-intercepts. -1, 0 and 1, 0 are my x-intercepts. You can remember that the name of the intercept is going to be the number that's not 0, which is also the axis that it's crossing. Sometimes when you're talking about the x-intercept, you care about the entire point. Sometimes you just care about the coordinate that's not 0. My open math usually cares about the entire point, but make sure that you're careful if it doesn't go in to just try the other option. So for example, you might say that the x-intercept is -1 and 1 because it's very clear that for the x-intercept, the y-coordinate would have to be 0. Sometimes we also care about symmetry in a graph. Symmetry we talked about a little bit with points last time, but we want to look at with an entire graph. The graph is symmetric if all of the points on that graph are symmetric. So in other words, we talked about what reflections would look like, and when I reflect across the axis or across the origin, the graph is symmetric if every single point, when I reflect it across the given thing, the axis or the origin, has the matching pair as part of the same graph. Taking a look at an example here, if I was to, let's say, sketch a graph like this, this graph would have symmetry over the y-axis Because if I look at any given point, it has a matching pair that was reflected properly. Now, one thing that we need to point out here, if I add one extra point, then even though every single thing on the green curve is symmetric over the y-axis, the fact that the blue one doesn't have its matching pair makes the entire graph not symmetric. Every single point needs to work. Now, that reason can make it somewhat complicated when you're trying to check whether or not a given graph has any symmetry. Because you can check hundreds or thousands or millions of points. You could check all of the points except for one, but that one point that didn't have symmetry makes it not symmetric. So for that reason, we'll need to be careful. The phrasing "for every" is the key word there. That means that if I'm trying to show that something is symmetric, I'm going to plug in a generic point rather than a specific one. So for example, I will use the definition and show that if I have x comma y, I'll also have negative x comma y. But to show that it's not symmetric, I just need a single point that doesn't work. In this case, I can use a specific counterexample. Finding a specific point, like pointing out the blue point in the previous example, would work out great. Let's take a look at a couple of examples here. Taking a look at this exact same function, we want to figure out whether or not the function is symmetric. Now we know the graph to this function, or we could figure out the graph to this function. You might even know what it would look like. But for now, let's figure out whether or not this function is symmetric by using the definition. So beginning here, I want to check if there are any points that will work to break it for any of the definitions. So first, let's say that I have the point if x equals 0. Let's figure out what it should be by using a table of values. So if x is 0, then I can plug in 0 plus 3 squared plus y squared is equal to 1. And let's see, 9 plus y squared equals 1. Y squared is negative 8. Oh, 0 is not even on this graph, so we'll cross that out. Sometimes it can take a couple of tries to find a point that works. Don't be afraid if that happens. Just keep trying until you find a better one. Maybe instead I should plug in 0 for y. Let's see what happens if I do that. If I plug in 0 for y, what I get is x plus 3 squared is equal to 1 because the y dropped as I put in 0. That means that I'm going to have taking the square root of both sides. And remember, anytime you take a square root, we need to add the plus or minus. X plus 3 is equal to plus or minus 1. We'll break off into two worlds. X plus 3 is 1, and x plus 3 is negative 1. That gives me x is equal negative 2 or negative 4. So I got two options here, negative 2, 0, and negative 4, 0. We can use this as a good starting point to look at some of my reflections. So let's first see what would happen. If I had the point negative 2 comma 0 and I reflected it so that it reflected across the vertical axis, with a vertical reflection, I should have the point 2 comma 0. Let's check and see if that works. 2 plus 3 squared plus 0 squared equals 1. Oh no, 25 does not equal 1. So I've just shown with one example that there is no vertical symmetry. Let's see if there's symmetry about the origin. In this case, it actually doesn't work, because if I had symmetry around the origin, negative 2, 0 should go to 2 comma 0. In this case, I flipped both x and y. Because y was 0, I don't have to flip it. 0 flipped is still 0. What I will need to be careful about is I'll need to be careful about checking for horizontal. Let's try that one on for size. For horizontal symmetry, negative 2, 0 should stay at negative 2, 0, and that one works. I also see that negative 4, 0, the other point that I have, would stay at negative 4, 0. Because I'm just flipping the y-coordinate, nothing is changing, and since the y-coordinate is 0, nothing does indeed change. So we're good here. We could check many other points and see whether or not this works, And we would find that all of them work, which would make us start to suspect that maybe there actually is some symmetry here. In order to show this for certain, we're going to need to do this with the equation. So let's double check and see what happens if I take the original equation and put the whole thing through a horizontal flip. This means I'm flipping the sign of y. So this becomes negative y squared. But remember that when I square something and it's negative, it just turns positive. So because when I went through the horizontal flip of the whole equation, I still had the same number, that's where we can go ahead and claim that we do indeed have the symmetry. So this equation does have horizontal symmetry. If you're staying with us for Pre-Calculus 2 or the back end of 167, we would eventually find out what this equation would make the graph of. A circle sitting right on the x-axis. That shows that we do have symmetry when I flip over the horizontal axis, but not when I flip over the vertical axis. That's all we've got for this lesson. All right, you guys have a fantastic day.